This is our second video for section 9.1 in our AP Statistics course. This is still really getting at describing and understanding what this idea of sampling distributions are. We're not quite actually calculating anything just yet. We're still looking to, in this case, describe what these sampling distributions are, what they look like, and what they tell us about the true populations. And if we look at this example here, it's based in the TV show Survivor. In this case, the specific season is the Guatemala season, which now is a long time ago, but it happened in 2005. Maybe some of you guys watched it back then. I don't think too many people really watch it now, but maybe they do. Now, if we were to look at this particular show, it says the true proportion of U.S. adults who watched it is 0.37, telling us that 37% of people watched that particular show in 2005. Now, if we look at this here, taking 1,000 SRSs of size 100, well, we see that, not surprisingly, it is centered at 0.37, proportion 0.37 there, okay? But we also see that it could be as low, these SRSs could be as low as 22% or as high as 52%. And what we're going to do today in this video, after we get through a couple of basic ideas, we're going to talk about, well, how can we narrow this? How can we decide what to do to make this a better sample? All right. But before we do that, let's talk about describing the distribution. And that's the same idea as it was back in chapter 1. So when we say shape, we are going to say that it is symmetric. As far as the center, we would say that the x bar of p hat is approximately 0.37. As far as the spread, well, we're not going to get into the standard deviation just yet, but we're going to say that the range is 0.52 minus 0.22, which is a whopping 0.3 or 30%. Okay, now that is clearly a big range and something that we need to address in just a little bit. But let's just again hold that thought for right now. So it says, notice a sample of size 100 gave a p hat pretty close to the p, which was 0.37, but it has a large spread. Is a sample of size 100 a trustworthy estimate for the population proportion, and why or why not? Well, if you were to be someone who would be interested in this, well, you would probably be someone who is an advertiser, and you're looking to buy time or sell time for different particular shows to, get your product out there, or to make money for the network if you are working for the network there. And you'd be able to charge quite a bit different money if you thought that 22% of the viewing audience were going to be tuned in, as opposed to someone else who might think that 52% of the viewing audience was tuned in. Okay? So basically, as it works, the higher the number of people or proportion of people who watch the show, the more money you can charge for the advertising. Think about the Super Bowl, where they charge millions and millions of dollars for a 30-second spot. Okay? But if only 22% of the people are watching the show, well, then you're going to not be able to charge nearly as much. All right? Now, let's take a look at the same example, still looking at 1,000 SRSs, but let's make that n, meaning the sample size, 1,000. As we see, it's still centered there at 0.37, and it still is approximately symmetric. So we would say, again, describing this new distribution, it is approximately symmetric. The mean of p hat is still 0.37, but where is the change? The change is in the range. Now, we could be as high as 0.43 or as low as 0.31. So what's our new range? Our new range is now only 0.12. It was 0.3 before, now it's 0.12. We could get an even clearer view if we were to zoom in or expand the scale and look at the one over here on the right. Now we can see more clearly that, yes, it's still in fact symmetric, and we can see a better view of the distribution there. Now they show here going 0.32 to 0.42, not drastically changing what we claimed to be the range in the previous example on the left. Same graph, left and right, just a zoomed in view on the right here. Okay, so what happened? We increased the sample size considerably, right? We went from 100 to 1,000, and our range, our variability, which therefore also means our variance and our standard deviation, got significantly smaller. All right, and that's a very, very important thing that we need to understand there. All right, now let's talk a little bit about the bias of a statistic, because that's something that's very, very important in when we are selecting a sample, or more specifically selecting a sampling distribution. We've talked about bias back in chapter 5, where basically something about how we collect the data makes it not representative of the population. Right? Now, if we were to think of that, then if we have bias in a statistic, then our sampling distribution is not going to tell us too much about the true population proportion, or mean, whatever the case might be here. So it says, how trustworthy is our statistic as an estimate of the parameter? Below are two sampling distributions of p hat for the samples of 100 and 1,000, the two examples we just did. And as we said, both of them were centered at that 0.37, which was the true p for that distribution. And what it says on the bottom here is that both of those sampling distributions are considered to be unbiased. And they're unbiased because their means equal to true proportion. So unbiased means that the mean of the sampling distribution is the same as the mean of the population proportion in this case, but it could be mean as well. All right. As a side note, which one has less variability? Well, clearly we know that the one with the larger sample size does. All right, but we're really focusing on this idea of the bias of the statistic here. And what we want to refer to is this definition up here. I'm going to put a star next to this definition again to remind you that is very important, very likely to see this as a test question at some point. An unbiased estimator, which is really the same thing as saying an unbiased statistic. An unbiased estimator is a statistic used to estimate a parameter as unbiased if the mean of the sampling distribution is equal to the true value of the parameter being estimated. The mean of the sampling distribution is equal to the true value of the parameter being estimated. The statistic is called an unbiased estimator of the parameter. So what that means is if you have the x bar of p hat is equal to p, then it's an unbiased estimator. Okay? That's what we're referring to there. And similarly, when we talk about the means, we'll see the same thing. If the mean of the sampling distribution is equal to mu, then it's also going to be an unbiased estimator. Okay? Now, that doesn't mean that it's always going to be that exact value, because sometimes we're going to get values below and above the true value of the parameter if we take many samples. But if we were to put them all together and look at the sampling distribution, then it's going to be centered at that value there. There's no favoritism, right? It's not leaning towards the lower side or leaning towards the higher side. It is going to be systematically centralized around that true value there. Okay? So unbiased estimator, another key vocabulary word for this video here. Now, let's talk a little bit about the variability of a statistic. This is a little bit of a conceptual idea here. But basically, what we're going to prove here through a concept exploration is that as you increase the sample size, the variability, the standard deviation of your sampling distribution is going to get smaller. Let's read here about the variability of a statistic. It says the variability of a statistic is described by the spread of its sampling distribution. This spread is determined by the sampling design and the size of the sample. Larger samples give smaller spread. That's pretty much a duh statement, common sense. And as long as the population is much larger than the sample, say at least 10 times as large, the spread of the sampling distribution is approximately the same for any population size. Does that sound familiar again? It should. Basically what that is saying there, if the population which we use a capital N for, is at least 10 times the sample size, little n, then the spread of the sampling distribution is approximately the same for any population size. All right, so that's our goal. Our goal is to have that be the case. All right, so it doesn't really necessarily depend on how large the population is. It really just matters how large your sample is. All right, and if we were to look at this example right here, this might help us to understand it through this concept exploration. So the survey of 1,200 people will have the same variability, whether the population being sampled is Freehold, New Jersey, San Francisco, or the entire United States. Now, if you think about that, 1,200 people in your sample, if you take those people out of Freehold, well, that's a much larger proportion of people than it would be if you were to take them from San Francisco or even the U.S. But what we're proving here, what we're trying to prove, is that the standard deviation, the variability, would be the same for all of them, because the variability is a product of sample size, not population size. So variability is determined by the sample size, not the population size. And this example down here, if you were to take, say you had a big barrel, and you were to take a big scoop of corn out of it, there's going to be some that are a little bit smaller, some that are going to be a little bit yellower, but it doesn't matter how big that barrel is, as long as you're taking your sample in a random fashion, right, and therefore your sample is representative of the population. It doesn't matter how much corn is around that scoop. It's still going to have the same variability, whether the scoop is the barrel is the size of, a wine barrel, or something that is the size of like an entire silo. Okay, it's not going to change. It's going to have that same variability there. All right. Now, let's get back to this idea of bias. All right, we've spent a little time with variability. Let's talk about the bias here. We can think of the true value of a parameter as the bullseye. Right. So the true value is the bullseye, hitting the dead center of that target there. And what we can do is we could refer to the bias and the variability as to, well, how are these points spread out around that target there. If the aim is off, meaning that it's not centrally located around the center of the bullseye, then that means that there is some kind of bias within the distribution, within the sampling distribution. If the shots are widely scattered, then that means that there is high variability within that sampling distribution. So let's look at a few examples here. If we look at example 1 right here, well, clearly they're not centered at the bullseye being right there in the center. They're not centered there. And if they're not centered there, then that means that there is some bias. And in fact, in this case, we would refer to this as high bias. But if we look at the points, they're rather close to each other. So what that means is that there is low variability because they're all very closely located within each other. So if we were to describe both the bias and the variability using the descriptors high and low, we would say this has high bias but low variability. High bias because it's not centrally located, low variability because it's very closely located where they are. So pause the video and try B, C, and D on your own. And again, using those descriptors high and low to describe the bias and the variability. If we were to look at example 2 here to describe the bias and the variability, well, the bias, would you say they are centrally located? Looks like they're fairly centrally located, so we would say low bias, but they're fairly spread out. So this one would be an example of low bias and high variability. If we look at example 3 here, are they centrally located? No, they're not, so there's high bias. Are they close together? Not that close together. So in this case, we have both high bias and high variability. And the last example, example 4 here, well, this is the ideal, isn't it? They're centrally located and they're very close together. This is low bias, and low variability. If you try to take your examples, your sampling distributions, and put it to this kind of test, this will help you understand whether your sampling distribution is a good estimate of the population or not. You have some examples that you're going to look at in class tomorrow, and as you see, we'll also be looking at a quiz. Now, not next class because we're going to be working on these examples here next class, but very soon we're going to be having a quiz on section 9.1. All right, and we'll see you guys very soon. Take care.